Hi everyone, welcome to this video. This video is basically a practice exam that for exam 1 that you have coming up soon. What I really want to do in this exam, or rather in this video, is just to show you the full exam attempt. You'll have the full 75 minutes to do it, and I just want to show you what to expect, how to answer the questions, and hopefully this will give you an idea to improve your own exam performance. As you see, the exam is of 75 minutes, 50 marks total, and 9 problems and 12 pages. There are two parts to this exam. Part one is conceptual question, and part two are long problems. So there are 6 conceptual questions and 3 long problems. And as written here, you will not be given any credit if you just select the answer in the multiple choice question. You have to give us an explanation. And even if you get the answer wrong, but your explanation is on the right track, we will award partial points. So please do make sure to kind of attempt the problems correctly and try to give us the solutions and your reasoning, and just don't leave them blank. And don't also spend too much time on each problem. Okay. So I will try to attempt it. I'll try to explain to you the problems and how I'm thinking about them, and hopefully that'll help you understand what's really how to think about problems and address them. And if there are questions, let me know. I should say, much like your exam, I would rate this practice exam as medium to a little bit difficult in terms of level. It is still all based on what we have covered in the course, but just so that you are kind of prepared of what to expect. Again, don't worry about the final grades, that will be all relative. So just make sure you're doing your best in this exam. All right, so let's start. So the first question is, what are the dimensions of rho v square by gamma? Rho is density, v is velocity, gamma is specific weight. And so this seems like a relatively simple, simple question. So density rho is, it's rho into v square by gamma. We know gamma is rho times g, which is specific weight, and you don't have to use this if you don't want to, but this is v square by g. And so from here, we can now go meter per second whole square and meter per second square. This implies this is meter square per second square by meter per second square. So this cancels out, so we get meters, which means it's just length. Okay. So relatively simple problem. You can have a little bit more complex functions, but really just simple dimensions. You apply, you get the answer. Okay. So this is the kind of work you can show when you're attempting the problem. Just simple writing down, and you don't have to be neat or anything, but just explain us what you're thinking, how you arrive at the answer. So let's keep going on. Okay, so now it says consider a stationary cylinder submerged inside water. Okay, so this cylinder is submerged inside water. So there's something about buoyancy force you can think about. It says, what is the direction of pressure force applied by the water on the curved face of this cylinder? So we have this curved face of the cylinder like this, right? This whole side. And we know there are 3 faces of the cylinder. There will be one face here, one force applying here, and then the net force on the top. The horizontal force will cancel out, and the net pressure force, as we know by water, should be buoyancy force, and that should be pointing upwards. So the net force should be upwards. So it simply should be positive C. Okay, so you can say buoyancy force is equal to force on curved surfaces, because the side faces just cancel out curved surfaces. So this is positive C. So simple, that's it. Note this is a little different because the cylinder is laying flat. It is not a vertical cylinder, which is what we did in the class, in which case the curved forces did cancel out, but in this case it's curved in this horizontal direction. So obviously there is net force positive up, because the pressure is actually down on the lower part of the curved surface. The pressure is higher, so that there is net force upwards, as it should be for buoyancy force. So again, a relatively hopefully clear reasoning and clear answer. All right, now let's keep going. So it says water with specific gamma 1 is flowing horizontally through a diverging duct. So the duct is diverging. The cross-sectional area is smaller here. So we can say, let's say this is point A, and then point B. We have been given that cross-sectional area. So let's call it 1 and 2 instead of 1 and 1 and 2. It's saying that P1, sorry, rather A1 is less than A2. Okay, that's very clear. The two vertical tubes are attached to ducts to measure the pressure in the left and the right of the duct respectively. So there are two tubes attached to them. And the left tube is filled with water only. So this field is only water. And the right tube is filled with water and another liquid specific weight gamma 2. Okay, so we have two specific weight things here, gamma 2. And which of the following statement is correct and why? You can either provide a physical explanation or a mathematical one. The dotted line indicate at equal vertical heights, indicate points at equal vertical heights. Okay. So basically, I mean, it's clearly a manometer problem. You can use Bernoulli's clearly like we have done before. So we know P1 plus rho V1 square by 2 plus gamma Z1 is equal to P2 plus rho V square by 2 plus gamma Z2. It's in the same vertical height, so this cancels out. And we know because A1 is less than A2, V1 is actually greater than V2. So V1 is actually greater than V2 because of continuity. This implies V1 is greater than V2. And simply this, it's not very difficult to see. P2 minus P1 is equal to rho V1 square by 2 minus rho V2 square by 2. And because V1 is greater than V2, so P2 is greater than P1. So it's pretty simple to see that when you're diverging, and as this is something we have discussed in the class, we expect, because in one inlet, one outlet, when something is diverging, we expect the pressure to be higher at this point 2 here, right? So we expect the pressure to be higher at point 2. So now when the pressure is higher at that point, we expect that the vertical weight of the vertical height attached in the system should be greater than the one on the left. So that's something we have discussed. So if the pressure is higher here, at point 2, this weight should be greater than the weight here. And for the weight to be greater than, because the height is the same, we should get gamma 2 by gamma 2 should be greater than gamma 1, because the net height is the same. So weight will be higher if the right-hand side has a higher weight fluid. So if gamma 2 is greater than gamma 1, we should expect this to be possible. So left tube, so right tube should have higher weight. Right vertical tube should have higher weight. So based on that, we get gamma 2 is greater than gamma 1. So pretty, hopefully, clear answer. So we have discussed this in class. It's just that now there are two fluids instead of one. So hopefully this is clear. All right, now let's go. You're given three velocity profiles, V1, V2, V3, and which we have been given a stream function. Which of the following have stream function given as x squared plus y squared is equal to c? So pretty clear question. So we have a velocity profile. We know how to calculate stream function. Stream function is calculated by dy by dx is equal to v by u. Yeah, this is the function of stream function. Dy by dx is equal to v by u. So for first case, dy by dx is equal to minus x by y. For this one, dy by dx is equal to x by x square plus y square square root minus y by x square plus y square square root. This cancels out. And then finally, in this one, dy by dx is equal to x by y minus 1. So first things first, it's very clear that all of them have dy by dx is equal to minus x by y. That's good. So the first thing is all of them will have the same stream function regardless. It could be all of the above or it could be none of the above. So we now go integrate. So we get y dy. We do an indefinite integral x dx plus some constant c1. It's pretty simple. So you get y squared by 2 is equal to minus x squared by 2 plus c1. So this simply becomes y squared plus x squared is equal to 2c1, but 2c1 could be just simply c. So we get x squared plus y squared equal to c. So we have all of the above. Okay. So pretty simple. Just be a bit careful when you're trying to calculate these things. but essentially the ratio is the same. So you will always get the same kind of, profile for all of them. So pretty straightforward, hopefully. All right, let's keep going. Okay, so now it says we have which of the following describes the velocity profile below. So we have velocity profile, and we have been asked to calculate which profile is the one that describes it. So let's start here. Something is in the center, so it's zero, but they're all zero, so that cannot really help us. So there is no velocity at the center, but then there is no velocity in the center from either of the formulas. We see here they're moving up, right and upwards. We see here they're moving right and upwards. We see they're moving right and upwards here. We see they're moving right and upwards here. So they are basically moving, all of them are moving right and upwards. So it's positive I, positive J always. So positive I, positive J always, there is only one that I see here, and that is this formula. So this should be the correct one because there is only one positive I, positive J, always positive I, positive J hat. Okay. So hopefully this makes sense. Let's keep going on. Okay, so we have another one on velocity profiles. Consider a velocity profile V hat is equal to xy plus I hat plus x squared j. Which of the following options correctly describe the acceleration in the fluid? So now we get to the local derivative problem. We know that a vector is equal to del u by del t plus v v dot del v vector. But this goes away. It's because there is no time dependence in the velocity. So I'll just simply write down the formula that we have discussed. You should remember is u del u by del x plus v del u by del y is ax, and ay is u del v by del x plus v del v by del y. Okay. So that's the answer. All right, so let's start from here. U del u by del x is u is xy, and del u by del x is y, so it's xy times y plus v is x square, and del u by del y is, so x square, and del u by del y is, so I mean hopefully this is clear, u is equal to xy, v is equal to x square. So del u by del y here, if I differentiate with respect to y, this is x. So this becomes xy square plus x cube. Xy square plus x cube. So I will only see one answer with that, but which is the first one. But let's keep checking. Hopefully we should get the second one as well to match, but let's keep going. Ay, u del v by del x, so u is xy. Del v by del x is del v by del x is 2x, so we get 2x square y plus v is x square plus del v by del y is 0 because it's only a function of x, so this goes away. So this becomes 2x square y. Yeah, so we get this first answer is option A. So hopefully this is clear. Simple question on using the formula for local and convective acceleration. Easy enough. You can get this to be just some differential calculus. All right, let's keep going further. All right, now we are giving consideration a stationary block with 6 centimeters, length 5 centimeters, and height 10 centimeters. Okay, total height 10 centimeters, submerged in a beaker filled with three liquids shown below. The height of the blocks H1, H2, and H3 are given. The densities are rho 1, rho 2, rho 3 are given. What is the density of solid block rho s and units gram per centimeter cube? Well, this is a relatively simple formula. I don't think this should be too complicated. If we assume some sort of an area here, so we can simply say, let's say area. So the buoyancy force simply is rho 3 H3A times gravity. So this is the volume submerged plus rho 2 H2A times gravity. Again, this is the volume submerged H2A times is the V2 and plus rho 3 H3A times gravity. This is the volume 3, and this should be equal to F gravity, and that is equal to rho S H1 plus H2 plus H3 times A times G. So this simply implies that rho S is equal to, if I equate now FB equal to FG, This is going to be in plus k hat, this is going to be minus k hat. So that's simply you get row 1 h1 plus row 2 h2 plus row 3 h3 plus row plus by h1 plus h2 plus h3. Okay, that's relatively easy. Okay, so row 1 h1, row 2 h2, row 3 h3. So we get and the units should come out to be just gram per centimeter cube. If I can just directly plug it in as well. Row 1 h1 is 4, row 2 h2 is 3, and 4 plus 3 plus 1, which is 4 plus 3 plus 1, 8. This is 8 by 10. This comes out to be 0.8 gram per centimeter cube. 0.8 grams per centimeter cube. So that makes kind of sense. Like we are getting some number 0.8 grams per centimeter cube for this density of solid. Okay, easy. This was actually quite easy. Now, what is the value of rho s if W is double to 12 centimeters without changing other parameters? So now they're saying, what if we increase the width? If we make this like twice, um, because our answer is basically just dependent on h's, it doesn't depend on width. We can say no change, same answer, same answer. Okay. Now for the same value of W and L, but a different combination of H1 and H3, a student calculates rho s of 0.45 gram per centimeter cube. Do you think their calculation is correct? Explain briefly. So they calculate the density of 0.45. So essentially they're calculating density of 45 through this formula, or some other formula they might have derived. And we have been given the value of rho s they find is 0.45. Now, the reason this kind of seems unclear and not possible is because the three densities we have been given are all above 0.5 gram, per 0.5 and above. So 0.45 you really cannot get. So the student is incorrect. The student is incorrect. Rho s has to fall between row 1, row 2, row 3. Row 1, row 2, row 3. So that's basically it. Okay, so they kind of miscalculate something. All right, so let's keep going. Now we have seventh problem. Was it seventh or this is the eighth problem? I think this is kind of maybe there's some error in the numbering here. This should be seventh problem, and this should be eighth problem. Okay, 12 points. It says water density rho 1000 kilogram per meter cube flows through a siphon. Okay, so it's going through a siphon and into a venturimeter in order to measure the rate at which the fluid leaves the reservoir. Okay, the outlet of the venturimeter is at atmospheric pressure. So the venturimeter part is outside the atmospheric pressure. The acceleration due to gravity is 10 meters per second. Find the velocity of the fluid at point 2, assuming that the height difference between point 1 and 2 is 1.25 meter as shown. The cross section of point 2 is 0.1 meter per second square. You can assume the velocity in the reservoir at point 1 is negligible. Okay, so basically it's saying point 1, we have to find the velocity at point 2, and then we have to assume that everything else is sort of simply the velocity v1 is negligible. So p1 plus rho v1 square by 2 plus gamma z1, p2 plus rho v2 square by 2 plus gamma z2. So P1 is PATM, P2 is PATM. So if it's PATM here, it should be PATM here as well, because there is no pressure drop because the velocity stays the constant. So sometimes students get confused. In a straight pipe of same cross section, in Bernoulli's does not give any drop in the pressure drop. So P2 is also PATM, P1 is PATM. We know it's gamma times rho times G times height is 1.2525 meters. I'll just call this h, small h. I prefer to kind of leave things in the variables rho vh. We have been given this, we can remove this as well. So we get rho v2 square by 2. And so rho gets cancelled out. So we get v2 is equal to root 2gh. Okay. So that's sort of the answer. So root 2gh. So it's 2 into 10 into 1.25. And so this becomes 20 into 1.25, which is 25 square root. So it becomes 5 meters per second. So a nice simple answer, 5 meters per second. You simply get root 2 GH because of the height. All right, now flow rate is also important. Flow rate is also been asked. Q is equal to A2 V2. So A2 is given to be 0.1 times 5 a second, and this is meter square, so it becomes 0.5 meter cube per second. So we have this as the answer, 5 meter per second, 5 meter cube per second. Should be hopefully clear. Okay, straightforward. Now, what is the velocity at flow rate at point 3? Okay, so this is finding the velocity at flow rate at point 3. So the velocity area is half, and the velocity should be double. So we know A3 V3 to A2 V2. So this implies V3 is equal to A2 by A3 V2. A2 is 0.1, A3 is 0.05, so it's double, twice of V2. So this just simply becomes 10 meter per second, and the flow rate is equal to flow rate is the same. Q is equal to Q2, so this is simply 0.5 meter cube per second. Okay. 0.5 meter cube per second. All right. Now it says, what is the value of capital H? The density of the liquid in manometer is 16,000 kilogram per meter cube. So it says this liquid here is 16,000 kilogram per meter cube. And what is the value of H there? Okay. So clearly, as we have discussed, if it's a wider duct or wider channel, then the pressure is one inlet and one outlet. The pressure is always higher at that point, which makes sense, which is why you have more liquid here. So first we have to calculate P2 minus P3. So we will do Bernoulli's at P2 minus P3. So P2 plus rho V2 square by 2 plus gamma Z2 is equal to P3 plus rho V3 square by 2 plus gamma Z3. So they are the same, we are the same level. And we know that P2 is higher than P3, which makes sense. P2 minus P3 is equal to rho into V3 square minus V2 square by 2. And this is equal to, as remember, it's always a difference in the weight. So instead of this part, we have this 16,001. So it's rho 2 minus rho 1 times G times capital H. So this is rho 1 rather. So rho 2 minus rho 1. I've been just using a rho, so I'll just keep calling it rho. If you want, you can call it a rho 1. It's just a simple substitution, rho 2 times rho capital H. Okay. So let's now plug in the numbers. So we have 1000 here. V3 was 100 square because this was 10 square. This is minus 25 by 2. Rho 2 is given to 16,000, so we have 15,000. Because this was 16,000, this was 1,000 into 10 into H. So first we'll calculate the thousands. We calculate this. We get, so 75 by 2 is equal to 150 times H. So capital H basically becomes 1 by 4 meters or 0.25 meters. We get this as the answer. Okay, so 0.25 meters. So it's a simple, nice calculation. You can use calculator or something if you want, but that's sort of the answer. That we have these two tanks and they're both open to atmosphere. So the pressures here are PATM and PADM. And the question says we have to show that gamma 1 is equal to gamma 2 for this to be balanced. Gamma 1 is equal to gamma 2. So what's really going on in the system? The pressure is essentially PATM. So if I go down here, the pressure here is going to be constant to the pressure here, right? So the pressure here is going to be the same as the pressure there. And we have been essentially asked to essentially suggest how to basically get gamma 1 is equal to gamma 2. So I mean, if I label this point as 1 and this as 2, you really have to show that the weight here, like if I'm going up, pressure decrease here, is equal to the pressure increase here. So that's essentially the idea. And we know that the pressure decrease. So like let's say P1, then we have this minus gamma, P1 minus gamma 1 L sine theta. So this is the sine theta parts. L sine theta minus gamma 2 L sine theta. That's easy, right? So that's simply P1 minus gamma 1 L sine theta minus gamma 2 L sine theta. Now then we'll start going down from here. We'll get plus gamma 2 2L cos theta. And then we have plus gamma 1. Now this height h is something I don't know. I know that height until this point. I don't know this height h. So one way to think about this is this height is this height, right? This I can calculate this height. I can calculate and subtract the 2L sine theta with this longer height, 4L cos theta, and then subtract from 2L cos theta. Okay, so it's a little bit tricky. So think about it. If geometry is not clear, let us know. But this is 2L cos theta minus of 4L cos theta minus 2L sine theta. Okay, so this is essentially what's going on. And now if we do this, and this is equal to P2, but P1 is equal to P2. So let's now collect the terms. So with gamma 1, I have minus gamma 1 L sine theta here. And then this will become minus 2L sine theta plus minus 2L cos theta plus 2L sine theta. So plus gamma 1 2L sine theta minus gamma 1 2L cos theta. This is essentially here what we get. And then we have here gamma 2 2L cos theta, gamma 2 2L cos theta minus gamma 2 L sine theta. Okay. So if you just rearrange this, essentially what you will see, you will get gamma 1 minus gamma 2 into 2L cos theta minus L sine theta is equal to 0. This is equal to 0. This cannot be 0, so this has to be 0. Gamma 1 is equal to gamma 2. Okay. So that's essentially what you get. Gamma 1 is equal to gamma 2. So that's kind of interesting. So essentially, you get this result that gamma 1 is equal to gamma 2 using trigonometry. Okay, so essentially hydrostatic questions using some trigonometry and so on. So hopefully this practice video was useful. If you have any questions, let us know, and we look forward to seeing you in the exam.